Hello, everyone. I would like to take this time to go over limits. So we have a review on limits. This way that you don't have to wait until midterm exam to review. You like to get started as soon as possible and constantly working on them so that you can make progress and be able to use this language to achieve your goal academically. So if you have any questions, then please bring them to classroom or send it my way. I'll be happy to answer those questions. I prepared this set of questions. Some of them are from our homework and some of them are from the textbook. And I also incorporated some pictures. And as we have covered all of these concepts, right? I just sent you the flashcards. How do we apply? How do we express? And how do we use the language properly to express your understanding and also to get points, right? For example, this is an example we saw from the textbook, okay? The number one thing we notice about function, okay? We'll talk about functions is domain. Although domain is not explicitly mentioned, but it is always there. It is always there. It affects our analysis of the question, okay? And as we understand for the intuitive definition of limit, when x is approaching a is not necessarily in the domain of the function, okay? So in some cases, you can see a is in the domain. In some cases, a is not in the domain. But we only consider when x is approaching a, the input approaching a, but not equals to a. And how do we see that, right? How do we see that dynamic process? So here's some examples. We went through many, many examples. And so this set of recording will, expand and will give you an opportunity to do a comparison from your own. And I will also send you the worksheet so you can study alongside of this recording. Okay, so here's the picture of the graph. Okay, f of x equals to x minus 1 over x squared minus 1. Immediately, we will be thinking of its domain, right? And what will be the domain? Of course, the domain x squared minus 1 cannot be 0. Cannot be 0. As a result, x cannot be, if you solve this equation, solve this inequality, x squared cannot be equal to 1, right? And as a result, x cannot be positive 1 or negative 1, right? So that's the domain. With that domain, we have this graph, right? Positive 1, negative 1. Now, the interesting thing about this graph is that we only are interested in the neighborhood of 1, okay? In the neighborhood of, let's see, this is in the neighborhood, yeah, for the limit of x equals to 1, right? And there's a negative 1 here, right? There's a negative 1 here. When you look at these limits, the limit of our interest, if I want to know the limit as x approaching positive 1, I certainly can make this a question, right? Then what do we do? Right? So we would have work with this rational function, right? We will work with this rational function and the function is x minus 1 Okay, factor x squared minus 1, we get x minus 1, multiply x plus 1, right? When x is approaching 1, but x is not equals to 1, so x minus 1 is not 0, so we can reduce it. We can reduce it. Okay, so when we reduce it, we will have 1 over x plus 1 left. Okay, so we can remove this parentheses. So now we can directly substitute. So what is that point, right? So by this time, we can get the number, which is 1/2. Direct substitution. Okay, one more step to show you. Okay, so this will be 1 plus 1. We no longer need the limit sign. So this is how you can express your word. Okay. But in the neighborhood of -1, what happens in the neighborhood of -1? Well, from the picture, you can see in the neighborhood of -1, and after the reduction, we cannot, right? So after we reduce it, right? If it's in the neighborhood of -1, right? We can still reduce this common factor, right? We can still reduce the factor, but here's -1, right? Well, what is the limit? Depending on which direction we approach, x is approaching -1. X could be approaching -1 from smaller than -1, right? It could be also approaching from larger. Okay, so it could be also approaching -1 from larger than -1. And you can see in this direction, it approaches positive infinity, and in the other direction, it approaches negative infinity. And how do we express them? How do we express it, right? We can express it in the following ways. This is the notation we have learned, right? This is the notation we have learned. So when we practice using them, we are getting better at using this language. Okay, so we're going to look at the limit from left, which is smaller than -1. Hold on. 195%. So you can see the negative sign here, right? If x is approaching -1 from smaller than -1, x approaching -1 from smaller than -1. So hold on, let me make enough space. Okay, let me make enough space so I can draw the picture and show it to you at the same time. Okay, or approaching -1 from larger. So what we see here is that in this picture, we have, let me find the arrow, right? When approaching -1 from smaller than -1, which is in this direction. And now you can see the output is approaching negative infinity. So this will be negative infinity. And the other one, it would be when x is approaching -1 from larger than -1, and that would be the output is approaching positive infinity. So now this is how we express. Okay, and the conclusion is that yes, x equals to -1 is the vertical asymptote, but the function does not have limits at -1. Okay, so what's the definition of a vertical asymptote? Right here, right? So two of the conditions at least one of the conditions is satisfied, right? So that makes it vertical asymptote. And then this is the time you can say, right, the limit from the left is not the same from the limit from the right. Okay, and if we ask the question, what is the limit of f of x when x is approaching -1? And you would say this limit does not exist. Do not leave blank. Okay, don't leave blank like this. Leave it empty like this. Okay, don't do this. Don't do this. Just put it a function or whatever the function in consideration out there. Okay, I saw this kind of mistake. Don't do. Don't. Do not. Don't do this. Okay, you need to. So I'll put it a note here. Okay, so when you study these examples, and of course, part of this work depends on what are the questions. What are the questions? Okay, the second one, this is a question from the textbook, right? So when we analyze and we try to find the domain, and what is the domain? The domain, obviously, denominator cannot be 0. Excuse me. Okay, so denominator cannot be 0. Okay, denominator cannot be 0. And then this is the graph. And what is the limit we're interested in? Well, if we're interested in the limit at any other number other than any number, okay, we could just do direct substitution if a is not 0. Okay, so in this case, you can, in a lot of other places, you can do direct substitution, right? If a is not 0, okay, that's not in the domain. But what if we are interested in the limit of the function when x is approaching 0? And this is another kind of question that when we consider this limit, right? This function obviously is very familiar to us. We have homework about it, right? So we will be bringing this function in, and we have a situation that when x is approaching 0, the numerator approaching 0, denominator approaching 0. We cannot do direct substitution. In fact, we cannot do anything unless we make some algebraic manipulation. So that algebraic manipulation, of course, is typically apply mathematical principle number 1, which you know, right? We multiply the conjugate of the numerator, right? So this is the so-called rationalizing the numerator. The goal is to transform the function so that we will no longer have the problem of 0 denominator. Okay, so very common technique. Now, we've done this before, so I'm going a little quicker. If you don't follow, just do rewind. And at the same time you're working this, you may like to have your flashcard scattered, or near you, so you can refer to those, flashcards. So numerator times numerator, denominator times denominator. So I'm going to multiply this piece, right, with x squared. Then you will need a parentheses. So this piece is gone. And this piece is going to multiply this top piece, so it's numerator times the numerator. Numerator times numerator, in this case, we can apply a plus b times a minus b, right? So we will get the following. Okay, so this piece squared minus 3 squared. Okay, this should be a pretty familiar process to you. So I'm just moving forward. Okay, I'm just moving forward. So this would make it, this is large enough. Okay, this should be large enough. Okay, and then we continue. Okay, so we got x squared plus 9. And this 3 squared is 9. And then we will get to x squared is left on the top because 9 minus 9 makes 0. And then x squared on the top and x squared in the bottom are reduced. Why? Because x approaching 0, but it is not equal to 0, right? So x squared is not 0, so we can reduce it. Principle number 1 once again. And this one can be removed, equal sign is not needed. Now we can substitute. Okay, direct substitution, which we can drop the limit, right? Replace x by 0. So the answer is 1/6, right? So we started with a function that when x is approaching 0, numerator approaching 0, denominator approaching 0, and the final limit is 1/6. If we look at the picture, right? If we look at the picture, what do we see? As x approaching 0 from smaller than 0, or x approaching 0 from larger than 0, and right here, right? There should be a little circle out here because it's undefined. Okay, that point is undefined. So I'm going to put a little circle, 0, 6. Okay. There's a red circle right there. This dot, okay? It is not defined, the function is not defined as at 0, but when x is approaching 0 from either side, the limit exists and it is 1/6. It is 1/6. Okay, so this is another example that we certainly don't have vertical asymptotes in this situation. Okay. And this is a very, very useful function. This is a very, very useful function. In the future, we're going to be working on this function. Okay, just take a look. The function f of x equals sine x over x. Okay, and of course, the domain is x not equal to 0. Right? Denominator cannot be 0. And what is the limit for this function? Okay, this limit for this function is, okay, this is a very important function. You can see from the graph, okay, we have sine x over x, the limit equals to 1. The limit equals to 1, okay? So let me draw the picture so you can see a bit more of the picture. Okay. There. So we also have an undefined point, and that point is because the function is undefined as 0. But when we have x approaching, when x is approaching 0 from either side of 0, okay, from smaller than 0 or from larger than 0, the limit is going to be 1. Okay, if you want to know more about this function, you can read about it in the book. If you have any questions, feel free to reach out to me. But this is the limit we want you just to know it. Okay, there's a proof, but you don't really need to know the proof. And this is a commonly used function, and we're going to come back to it another time. Okay, then you say, how about if a is not 0? And we're considering the limit for this function. Or in those cases, you can just do direct substitution. You can just do direct substitution. Okay. Now, question number 4. This is a situation that the function as x is approaching 0, okay, the function is just bouncing between -1 and +1. We got a better picture. This picture is from the textbook. Okay, this picture is from the textbook. When I have the software to graph it, the software doesn't do a very good job. So this software is not perfect. It's pretty convenient and helpful for me to use it in the classroom, but it is not super. The graph it produces is not super smooth. Okay, so this is the situation. We can say the function doesn't have a limit. Okay, as x is approaching 0, pi over x is approaching either, depending on x is approaching 0 from left or right, the sign of pi over x is just bouncing between -1 and +1 because the range of sign is bouncing. The range of sign is from -1 to +1. So this is the case. We say limit does not exist. We say limit does not exist. Okay, and of course the domain is the same. X is not equal to 0. Okay, and this function is from textbook. This function is from a textbook, and it's a piecewise function. We have two pieces, right? Everywhere else, right? For any a other than 0, the limit is either 0 or 1. But for 0, right? For 0, of course, you can tell when we approach, this is the time you're going to have to use limit from left or limit from right. So if we consider limit when x is approaching 0 from smaller than 0, okay, I'm making some adjustments so you can see the sign, right? So from the picture, right, when we're approaching 0 from smaller than 0, which piece of function we're using? This piece, right? So that's going to be 0. If we look at the limit of function when x is approaching 0 from larger than 0, and that limit is going to be equals to 1. So you can see this is a commonly used language. When these two limits both exist but not equal, then the function has no limit. Limit does not exist. So this is the language you use and you learn to use. And it's very effective. It will get you points. It will get you the points. Then you will say, this limit does not exist. Okay. And we went over, so you can see this is how the format of how to make your case and get the points you want. Okay. Infinite limits. Okay, we talk about it. Okay, we talk about infinite limit, and so we covered this in class. And let me just write it down one more time. Okay, so limits as x approaching 0. You see, in this case, we do not need to consider limit from the side, because 1 over x squared, no matter what the sign of x, after you square it, it's going to be, it's going to be positive infinity. Okay, this is positive infinity. Refer to flashcards. We have this piece, right? When x is approaching a from either side, and the function approaches infinity. So this is called infinite limits, right? The other flashcard approaching negative infinity when x is approaching a from either side. So we have these, you have these in your textbook, and you also have the flashcards. Okay, and how do we express it? How do we express it, right? The following questions, they are from the homework that in week 4, okay, in week 4. So when x is approaching 0, so the picture could help us, okay? The picture could help us when x is approaching. I think I should make the picture a little bit smaller. Otherwise, it takes up so much space. Okay. If we're not thinking about domain, then, right, if we're not thinking of a domain, then you say, well, what's the domain? You still have to, if A is not 3, right? So the rest of it is just direct substitution. The domain here is x is not equal to 3. X is not equal to 3. Okay, so if you have if you want to find a limit, say you have a question, limit is approaching a number other than 3, they're all direct substitution. But what if it's approaching 3, right? Then in this case, you have to look at limit from left, from right. And the narrative, the common narrative would be, right, the limit from left, which is 3 raised to the power, you put a negative sign on the shoulder. Okay, when x is approaching 3 from smaller than 3. So in that case, function approaches negative infinity. So this limit is negative infinity. Okay, you can put a semicolon, and then you will consider the limit when x is approaching 3 from larger than 3. And of course, you can see that limit. Okay, right here. Then the function approaches positive infinity. Approaches positive infinity. Okay, limit from left and limit from the right, they're not the same. Okay, so let me clean this up. Okay, so these two limits are not the same. So you can say the limit when x approaching 3 does not exist. In fact, in this case, it is demonstrated x equals 3 is a vertical asymptote. Okay, the tangent situation we have discussed in class, and we have all these other pictures here. I think I'm going to send this to you, and I don't want to make this too long. And I also need a break myself. So until next time, thank you for watching.